In this video, I plan to go through the questions we did in class this morning. So we started the class with some revision questions. So the first question I gave you was sine 15 degrees. So to solve sine 15 degrees, I wanted you to use the sums and differences rule. So we'll start off with sine 15 degrees. We know sine 15 degrees can be broken up as sine brackets 60 minus 45. So if I can break 15 degrees into 60 degrees minus 45 degrees, I can use the differences rule to work that out. So using the differences between two angles for sine, we get sine 60 times cos 45 minus cos 60 sine 45. So since this question was express it as an exact value, sine 60 is root 3 on 2, and cos 45 is 1 on root 2. Cos 60 was a half, sine 45 was 1 on root 2. So root 3 times 1 gives you root 3, and 2 times root 2 is 2 root 2. 1 times 1 is just 1, and 2 times root 2 is 2 root 2. Since they have the same denominators, we can just subtract our numerators. And this is our final answer. So just remember your exact values, and if you can't do that, refer back to the diagrams I've shown you in our 2-unit classes, and also that tip I told you about in class this morning about using your calculator. So moving on to our second question. So the second question we did in that lesson was tan 105. So we are going to break up 105 into 60 and 45 again. So tan 105 is the same as tan 60 plus 45 degrees. So using the sums of tan degrees, we get tan 60 plus tan 45 all over 1 minus tan 60 times tan 45. So tan 60 is root 3 as an exact value, and tan 45 is over 1. 1 subtract tan 60 once again is root 3, and tan 45 is 1. So I'm just simplifying all this. This is what you get as your final answer. If you want to rationalize this, then we need to multiply both the numerator and the denominator by the conjugate surd. So the conjugate surd is the same two terms as the denominator, except we've changed that minus sign into a plus. So what we have here is root 3 plus 1 brackets times 1 plus root 3 all over 1 minus 3. So I'm going to scroll over to get some more space. Okay, so we have two binomials, so we'll expand the binomials. Root 3 times 1, root 3. Root 3 times root 3 equals to 3. 1 times 1 is 1. And 1 times root 3 gives you root 3 all over 1 minus 3, which is minus 2. So scrolling over again, collecting like terms. Okay, scrolling over, collecting like terms, we get 2 root 3 plus 4 all over negative 2. We'll simplify the top bit as 2 brackets root 3 plus 2 all over negative 2. And if I divide both sides by 2 to simplify it, I should get 1 brackets root 3 plus 2 all over negative 1. And once again, to get rid of the negative 1 in the denominator, we just put it on top. So it's negative 1 brackets root 3 plus 2. And if you want, you can leave it as root 3 minus 2. Okay, so that's the final answer. I was actually happy with just this solution up here. Unless the question tells you to rationalize your denominator, you don't really need to do all these steps. Okay, so moving on to our next question. So our next question was sine 3a. It was sine 3 theta in your exercise book, but I couldn't find the theta button on the laptop, so it's sine 3a for now. So sine 3a is the same as sine 2a plus a. So we're going to use the sums formula for this one. So it's going to be sine 2a cos a plus cos 2a sine a. So we don't really want these double angles, so we're going to substitute them. So the double angle for sine 2a is 2 sine a cos a. And that's all of that is still multiplied by cos a. And we're going to change cos 2a to a version that has sine in it. So the version that we're going to change this into is 1 minus 2 sine squared a bracket sine a. So we still have sine a in the bottom at the end. So multiplying, it gives you sine a cos squared a, because the two cos multiply to give you cos squared, plus sine a brackets, sorry, not bracket, minus 2 sine cube a. So now what I want to get rid of is I want to get rid of this cos squared now. So to get rid of that, I'll just use the 2-unit trig identity. So the 2-unit trig identity for cos squared a is 1 minus sine squared a. So we still have the sine a by itself, and we still have 2 sine cubed a. So expanding that, I have 2 sine a minus 2 sine cubed a plus sine a minus 2 sine cubed a. So collecting like terms, that gives you 3 sine a minus 4 sine cubed a. You may have different variations to the working out of this question, but as long as you get this final answer, you should get your full marks if I was to give you this question in an exam. So our next question was expand cos 3a, and it's just expand it in terms of just cos a. So once again, we're going to break this up into cos 2a plus a. It's just cos first term, so cos 2a times the cos of the second term, cos a minus sine of the first term, 2a, times the sine of the second term, a. Once again, we don't want the double angles, so we are going to change them. So remember, this is in terms of cos a. So I'm going to change cos 2a into a version that has just cos in it. So the version that has just cos for cos 2a is 2 cos squared a minus 1. And we're still timesing all that to cos a because that term is still there. I'm going to change sine 2a into 2 sine a cos a. All this is still times to sine a. Expanding that gives you 2 cos cube a minus cos a, so that's a lone term, minus 2 sine squared a cos a. I'm going to change sine squared a into 1 minus cos squared a. So we still have our first term as is, our second term as is. Now it's going to be changed, so 2 remains the same, but sine squared a is going to be changed into 1 minus cos squared a times cos a. So this is not very neat. We want to make it neater, so I'm going to move cos a to here. So 2 cos cubed a minus cos a minus 2 cos a brackets 1 minus cos squared A. And if we have that, we can expand and collect like terms because it looks like I only have cos left. It's negative cos 2A, so negative 2 cos A times negative cos squared A becomes positive 2 cos cube A. So collecting like terms, these two are the same. And these two terms are the same. We get 4 cos cubed A minus 3 cos A.